At 05:30 hours on December 16th, 1944, Colonel George Axelson stood in the Fire Direction Center of the 406th Field Artillery Group near Monschau, Germany, and listened to something that would change his life forever. The radio crackled with panic. Voices screamed through static. The 38th Cavalry Squadron was being overrun by German infantry advancing through the pre-dawn darkness of the Ardennes Forest. The lightly armed cavalry troopers were dying. They needed artillery support immediately, or they would be annihilated. Axelson had exactly what they needed. Sitting in ammunition storage bunkers behind his position were wooden crates, marked with red bands and stenciled with a single word in white paint: POZIT. Inside those crates were artillery shells unlike any that had ever been fired on the continent of Europe. Each shell contained a miniature electronic brain no larger than a man's thumb, a device so sophisticated that German scientists had declared it impossible to build, so secret that it carried the same security classification as the atomic bomb project being developed in the New Mexico desert. These shells could detonate in mid-air above enemy troops, turning near misses into certain kills. Foxholes offered no protection. Trenches became death traps. Soldiers who felt safe behind log-reinforced bunkers would be cut down by fragments raining from above. But there was one catastrophic problem. Supreme Commander Dwight Eisenhower had not authorized their use. The Pentagon had forbidden American artillery units from firing these shells over land. The fear was absolute and specific. If a single dud shell fell into German hands, enemy engineers might reverse engineer the technology. They might develop countermeasures that could blind Allied radar. They might create their own proximity-fused anti-aircraft shells that would devastate the bomber formations flying over Germany every day, killing thousands of Allied airmen. Using these shells without authorization could result in a court-martial. Axelson would be relieving himself of command. He would be destroying his career. He would be violating a direct order from the highest levels of Allied command. The radio call came again. The cavalry squadron was being slaughtered. Axelson made his decision in seconds. Men were dying. Regulations could wait. He turned to his gun crews and gave an order that would echo through military history. Load, POZIT. Open fire. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Minutes later, the first proximity-fused shells screamed over German infantry positions and detonated 30 feet above the ground. The German soldiers advancing on the 38th Cavalry Squadron suddenly found themselves engulfed in steel rain falling from empty sky. Fragments traveling at thousands of feet per second penetrated helmets, tore through winter uniforms, and shredded exposed flesh. Foxholes that should have provided protection became graves. Log-reinforced positions that would have stopped conventional artillery fire were penetrated by high-velocity fragments arriving from directly above. Men who had felt safe in covered positions were cut down by explosions they could not see coming and could not understand. The German attack stalled immediately. Then it collapsed entirely. What Colonel Axelson did not know was that he had just fired the first land-based proximity-fused artillery shells in the European theatre. What the Germans being killed by those shells did not know was that they were facing a weapon their best scientists had examined and dismissed as Allied propaganda. The shells exploding above their heads contained miniature radar sets more sophisticated than anything Germany had been able to build. Each shell carried electronic components that should have been pulverized by the Selasers, forces of being fired from a cannon. Each shell made targeting decisions autonomously, without any human intervention, adjusting its detonation point in real time based on what it sensed in its environment. This was not just a new weapon. This was a fundamental transformation in how warfare would be conducted for the next 80 years. This is the story of how American physicists created that impossible device. How they miniaturized technology that normally required equipment the size of a room into a package smaller than a beer can. How they kept the project secret for 3 years, while coordinating the work of more than 100 factories and 10,000 workers across the United States. How that technology killed 702 Germans in a single artillery barrage and forced military commanders to completely rethink the tactics of land warfare. and how the entire project almost didn't happen because university trustees refused to sponsor research they weren't allowed to know anything about. The problem started long before December 16th, 1944. It started on December 7th, 1941, when Japanese aircraft attacked Pearl Harbor. American anti-aircraft guns opened fire that morning with everything they had. They threw thousands of shells equipped with timed fuses into the sky above Hawaii. These fuses were supposed to detonate at specific altitudes, creating walls of shrapnel that enemy aircraft would fly through. The system required gunners to estimate the altitude and speed of incoming aircraft, calculate the time of flight for each shell, set the fuse mechanically before loading, and hope everything worked correctly. It rarely did. Of the 48 civilians killed at Pearl Harbor that day, most died when improperly fused American anti-aircraft shells exploded on impact with the ground in downtown Honolulu instead of in the air near Japanese attackers. The shells that did explode at the correct altitude rarely hit to anything. The statistics were worse than grim. They were catastrophic. In the worst cases during the early war period, American gunners fired more than 1,000 shells for every enemy aircraft destroyed. Even under good conditions, hitting a fast-moving aircraft at altitude with time-fused shells was nearly impossible. That was not a defensive weapon. That was ammunition expenditure with occasional accidental success. The United States Navy understood they had a problem that would get men killed in enormous numbers. Modern aircraft were too fast, too maneuverable, and flew at altitudes that made accurate time fusing nearly impossible. Japanese pilots had demonstrated at Pearl Harbor that they could attack with near impunity. American ships operating without air cover in the Pacific were floating coffins. Gunners needed a fuse that would automatically detonate when a shell came close to an enemy aircraft. They needed a proximity fuse. The concept was not new. Multiple nations had explored the idea for years. Every attempt had failed because the engineering challenges seemed genuinely insurmountable. To work effectively, a proximity fuse needed to sense when it was near a target and detonate automatically. That meant incorporating some kind of electronic sensor into the nose of an artillery shell. But artillery shells experienced forces that destroyed conventional electronics instantly. When fired from a 5-inch naval gun, a shell accelerated to 2,800 feet per second in the length of the gun barrel. That created a setback force of 20,000 times the force of gravity. 20,000 G-forces acting on electronic components designed for radios and laboratory equipment. Simultaneously, the rifling grooves in the gun barrel spun the shell at 25,000 revolutions per minute to stabilize its flight. Any electronic components inside the shell would be subjected to crushing acceleration, violent rotation, and impact forces that would pulverize ordinary vacuum tubes into glass powder and metal fragments. Then there were the practical requirements that made the problem even more impossible. The fuse needed to be small enough to fit inside the nose of a standard artillery shell, typically about 3 inches in diameter. It needed to be reliable enough for mass production by workers who had never built anything like it before. It needed safety mechanisms to prevent premature detonation that could kill friendly gun crews loading the shells. It needed to be weatherproof and stable in storage for months in tropical heat and Arctic cold. It needed to work in rain, in fog, at night, in conditions where visibility was zero, and critically, it needed to be simple enough that ordinary sailors with basic training could handle it safely without specialized education in electronics or physics. It needed to be cheap enough to manufacture by the millions because thousands would be fired in every major engagement. German scientists had been working on proximity fuses since the early 1930s. By 1944, they had explored more than 30 different designs, including acoustic fuses triggered by engine sounds, electrostatic field detection systems, and radio frequency approaches similar to what the Americans would eventually develop. None worked reliably under combat conditions. In 1943, German engineers reached a definitive conclusion after more than a decade of research. Building a vacuum tube-based radio fuse for artillery shells was technologically impossible. The acceleration forces would destroy the tubes before the shell even left the gun barrel. The problem could not be solved with existing technology. The German military moved on to other projects. British scientists reached a different conclusion. Starting in 1939, researchers at PIE Limited began developing ruggedized vacuum tubes that could withstand high acceleration forces. By 1940, they had working prototypes of proximity fuses for unrotated projectiles, which was the British cover name for solid-fueled rockets. Rockets had relatively gentle acceleration compared to artillery shells fired from guns, so the electronic components faced far less mechanical stress. The British fuses worked adequately in rockets launched from ground-based launchers, but attempts to adapt the same technology for high-velocity artillery consistently failed. The vacuum tubes shattered. The circuits failed. The fuses were unreliable at best and completely non-functional at worst. In August 1940, a British technical mission led by Sir Henry Tizard arrived in the United States, carrying a black metal deed box. Inside that box were some of Britain's most closely guarded military technologies. Among the items packed carefully in foam were circuit diagrams and physical prototypes of British proximity fuse designs. The British hoped that American industrial capacity could solve manufacturing problems that British industry could not overcome alone. Britain was fighting for its survival. London was being bombed nightly by the Luftwaffe. British scientists had developed brilliant concepts, but they lacked the industrial base to turn those concepts into weapons that could be produced at the scale needed to change the outcome of the war. The National Defense Research Committee assigned the Proximity Fuse Project to Section T of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington, District of Columbia. Section T was led by Dr. Merle Tuve, a physicist who had helped develop the theoretical foundations for radar technology in the 1920s. Tuve understood immediately that the core technical challenge was not conceptual. The concept was simple. Every physicist understood how radar worked. The challenge was execution. Radio proximity fuses were conceptually straightforward. A miniature transmitter in the nose of the shell would emit radio waves. When those waves reflected off a nearby target, a receiver circuit would detect the reflected signal and trigger a detonator. Simple concept. Extraordinarily difficult engineering. Tuve assembled a team of physicists and engineers and gave them an impossible deadline. The Navy needed working proximity fuses for 5-inch anti-aircraft guns as soon as physically possible. Japanese air power was sinking American ships across the Pacific. Without an effective anti-aircraft defense, the Navy could not operate safely in contested waters. The American Pacific Fleet was trapped in Pearl Harbor while Japanese forces conquered the Philippines, Malaya, Singapore, and the Dutch East Indies. Every week without a working proximity fuse meant more American sailors would die when their ships were attacked by aircraft their guns could not hit. Tuve's team had months, not years, to solve problems that had stumped British and German scientists for more than a decade. The team Tuve assembled included some of the brightest minds in American physics and engineering. Richard Roberts and Henry Porter conducted experiments on circuit designs that could survive being fired from guns. Robert Broad worked on receiver sensitivity, trying to develop circuits that could detect faint radar echoes while the shell spun at 25,000 revolutions per minute. Harry Diamond and Wilbur Hinman from the National Bureau of Standards developed parallel fuse designs for rockets and bombs, which faced different but equally difficult engineering challenges. The collaboration brought together academic researchers who understood the theoretical physics, government scientists who understood military requirements, and industrial engineers who understood how to manufacture complex devices at scale. Every member of the team understood they were racing against time. American sailors were dying in the Pacific while they worked through technical problems in Maryland laboratories. The first breakthrough came from Lloyd Berkner, one of Tuve's engineers. Berkner developed a system using separate transmitter and receiver circuits instead of a combined transceiver. This simplified the electronics significantly and made the entire system more reliable. Separate circuits meant each component could be optimized independently. The transmitter could be designed purely for power output, The receiver could be designed purely for sensitivity. But the vacuum tube problem remained completely unsolved. Standard vacuum tubes shattered under the acceleration forces of gunfire. The glass envelopes cracked like eggshells. The filaments broke into pieces. The internal tube elements came loose from their mounts and destroyed the circuits they were supposed to power. The solution came from an unexpected direction. Western Electric Company and Raytheon manufactured miniature vacuum tubes for civilian hearing aids. Hearing aid tubes were already ruggedized for portable use in devices that would be dropped, jarred, and subjected to daily mechanical stress. They were small, mechanically robust, and used relatively little electrical power compared to standard radio tubes. Working with Tuve's specifications, Western Electric and Raytheon engineers began modifying hearing aid tube designs to survive artillery gun firing. They reinforced the glass envelopes with thicker walls. They redesigned the filament mounts to absorb shock. They tested prototype tubes by firing them from air cannons into solid blocks of wood, subjecting the tubes to acceleration forces far exceeding what they would experience in actual combat use. Most tubes failed catastrophically. The engineers redesigned them based on failure analysis. They tested the new designs. Those failed too. They redesigned again. The process was brutally iterative. Each design cycle required weeks of work. Each test firing destroyed dozens of expensive prototype tubes. The engineers were working against a countdown clock. Every day of delay meant more American ships sailing into combat without adequate air defense. By January 1942, after months of iterative testing and continuous redesign, they finally had vacuum tubes that could survive 20,000 G-forces and 25,000 revolutions per minute spin rates. The tubes were tiny, barely larger than a rifle cartridge. Each proximity fuse required 4 of these miniature tubes, along with resistors, capacitors, a battery, safety mechanisms, and a detonator. All of this had to be packed into a space smaller than a beer can and weigh less than 2 pounds. The battery system alone presented enormous engineering challenges that almost killed the entire project. Standard batteries could not withstand the firing shock. The violent acceleration would crack battery casings, rupture internal plates, and spill corrosive electrolyte throughout the fuse assembly. Engineers developed a revolutionary reserve battery design that remained completely inert during handling and storage. The battery was activated only by the setback force of firing. A small glass ampule containing liquid electrolyte was positioned inside the battery housing. When the shell was fired, the 20,000 G acceleration force shattered the glass ampule instantly. The electrolyte flooded the battery plates and activated the power supply within milliseconds. This meant the battery had effectively unlimited shelf life and could not accidentally activate during transportation or loading. The safety mechanisms required equally innovative engineering solutions. The fuse needed to remain completely inert and safe during all handling, transportation through combat zones, and loading into gun barrels. It could not arm until the shell had travelled far enough from the gun to protect friendly forces from premature detonation. Engineers designed a complex multi-stage safety system using mercury switches that required centrifugal force from the shell's rotation to close electrical contacts. The mercury switches would only close when the shell was spinning at a specific rate, which only occurred after the shell left the gun barrel. Combined with this was an electronic timer circuit that ensured at least 0.3 of a second elapsed after firing before the fuse could possibly detonate. 0.3 of a second meant the shell had travelled at least 750 feet from the gun before it became active. Even if a shell misfired and tumbled out of the gun barrel onto the deck near the crew, it would remain completely harmless because the safety systems would never arm. In early August 1942, the Navy conducted the first live fire test of proximity-fused shells in the Chesapeake Bay. The cruiser USS Cleveland fired at radio-controlled drone aircraft on August 12 during its shakedown cruise. The test was scheduled to run for 2 days with multiple drone targets. The test ended after 1 day because all the drone aircraft were destroyed almost immediately. The gun crews aboard Cleveland fired 4 proximity-fused shells at maneuvering drone targets. 3 drones were completely destroyed. Navy observers present at the test were genuinely astonished by the results they were witnessing. The proximity fuses worked perfectly under real combat conditions. For the first time in naval history, anti-aircraft gunners could reliably hit moving aerial targets without achieving direct hits. The shells just needed to pass within 70 feet of a target, and the proximity fuse would detonate automatically, shredding the target with thousands of high-velocity fragments. The improvement over time-fused shells was so dramatic that some Navy officers initially suspected the test had been rigged or manipulated to produce misleading results. How could a device this small, this complex, work so reliably? Subsequent tests with additional drone targets confirmed the initial findings beyond any doubt. The proximity fuse represented a genuine revolutionary breakthrough in anti-aircraft warfare. It was not incremental improvement, it was transformation. But successful testing and actual combat deployment were completely different challenges. Tuve's team needed to scale up from hand-built laboratory prototypes to mass manufacturing at industrial scale. By January 1943, Section T had moved from the cramped laboratories at the Carnegie Institution to a much larger facility in Silver Spring, Maryland, and been reorganized as the Applied Physics Laboratory under Johns Hopkins University, with Tuve as founding director. The organizational transformation had been dramatic and reflected the scale of what was being attempted. The project now involved 26 major contractors and more than 10,000 workers spread across the United States. More than 100 American companies contributed components to proximity fuse production, including General Electric, RCA, Raytheon, Sylvania, Westinghouse, Eastman Kodak, Zenith, Philco, and even Wurlitzer, the organ manufacturer, which converted its barrel organ factory in North Tonawanda, New York, into an electronics assembly facility. Each proximity fuse contained 130 miniaturized electronic components. Assembly required precision work performed under magnification by workers with steady hands and extraordinary patience. Workers at factories across America built these fuses without knowing what they were building. Security was absolute and ruthlessly enforced. The project had the same classification level as the Manhattan Project, developing the atomic bomb. Workers who asked supervisors what the fuses were for were told only that they were critical to winning the war and that asking questions about the work was forbidden. Many workers never learned the truth about what they had been building until after the war ended in 1945. The Crosley Corporation in Cincinnati, Ohio, became one of the largest proximity fuse manufacturers, ultimately producing 5.2 million units, roughly 24% of total wartime production. The company converted its entire manufacturing operation from civilian consumer products to war production. General Electric's Christmas tree lamp factory in Cleveland, Ohio, was retooled specifically to produce miniature vacuum tubes using modified hearing aid tube designs. Eastman Kodak, which normally manufactured cameras and photographic film, began producing precision electronic components. RCA and Sylvania joined the massive production effort, each contributing specialized components that no other manufacturer could produce. At peak production in late 1944, American factories were manufacturing more than 100,000 proximity fuses per week. The economic transformation was staggering. The fuses that cost $732 each in early 1942 cost just $18 each by 1945. That price reduction reflected both improved manufacturing efficiency and the economies of scale that only American industrial capacity could achieve. No other nation on Earth could have coordinated this level of industrial mobilization while simultaneously fighting wars across two oceans. In November 1942, the Navy shipped 5,000 proximity fuses to Pearl Harbor. The Pacific Fleet received 4,500 of them and began distributing the shells to ships operating in the Solomon Islands near Guadalcanal. But the fuses came with strict and non-negotiable restrictions. They could only be used over open ocean water where dud shells that failed to detonate would sink to the ocean floor, placing them permanently beyond enemy reach. If a fuse failed to detonate and fell on land controlled by Japanese forces, enemy engineers might recover the intact shell and reverse engineer the technology. That risk was considered absolutely unacceptable by Pentagon planners. Every ship carrying proximity-fused ammunition received orders to destroy their entire supply of these shells, rather than allow them to be captured if the ship was in danger of being boarded or sinking in shallow water. On January 5, 1943, those restrictions were tested under actual combat conditions. The light cruiser USS Helena was operating off Cape Hunter on the south coast of Guadalcanal when Japanese dive bombers attacked the American task force. After dropping their bombs on ships maneuvering below, the aircraft pulled up and began climbing away at high speed. Lieutenant Red Cochran commanded Helena's aft 5-inch battery. He ordered his gun crews to fire 3 salvos of proximity-fused shells at the departing aircraft. The gun crews had minimal time to aim. The aircraft was already several thousand feet away and climbing fast, accelerating toward escape velocity. Under normal circumstances with time-fused ammunition, this would have been an impossible shot. The aircraft was too far away, moving too fast, and the gunners had no accurate way to calculate the proper fuse setting. All 3 proximity-fused shells exploded in the air near the dive bomber. The aircraft disintegrated and fell into the ocean in burning pieces. Helena's crew had achieved the first confirmed kill of an enemy aircraft using a proximity-fused shell in combat. It was not luck. It was repeatable technology that would work every single time conditions were similar. Over the next 12 months, the effectiveness of proximity fuses in naval combat became statistically undeniable. In 1943, Navy ships fired 9,128 proximity-fused rounds and destroyed 61 enemy aircraft. That represented 1 kill for every 155 shells fired. The old time-fused shells had required 508 rounds per kill on average. The proximity fuse was more than 3 times as effective, and this was just the beginning of a transformation in naval warfare. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. As gun crews gained combat experience with the new fuses and shipboard fire control systems improved through iterative refinement, the kill ratios continued improving dramatically. By 1944, the number of proximity-fused rounds fired climbed to 32,826 shells, accounting for hundreds of Japanese aircraft destroyed across the Pacific theater. During the Marianas Campaign in summer 1944, proximity-fused 5-inch shells provided critical air defense for carrier task forces operating deep inside Japanese-controlled waters, far beyond the range of land-based fighter support. During the Battle of the Philippine Sea in June 1944, American ships equipped with proximity fuses shot down numerous Japanese aircraft attempting to attack the carriers that formed the core of American naval power in the Pacific. The Japanese naval aviators attacking American ships were among the most experienced pilots remaining in the Imperial Japanese Navy. They had survived years of combat. They understood American tactics. They knew how to evade anti-aircraft fire. But they found themselves unable to penetrate the defensive screen created by proximity-fused anti-aircraft shells that detonated automatically whenever they passed near aircraft. One Navy operational research study concluded that for every enemy plane destroyed before proximity fuses were deployed, 5-inch guns had needed to fire approximately 1,000 time-fused shells. With proximity fuses widely deployed, that number dropped to about 250 shells per kill. This represented a 4-fold improvement in combat effectiveness, which translated directly into American sailors surviving battles that would have killed them with conventional ammunition. On May 11, 1945, the destroyer USS Hugh W. Hadley was stationed on radar picket duty off Okinawa when more than 150 Japanese aircraft attacked in a coordinated strike designed to overwhelm defensive fire through sheer numbers. Hadley's 5-inch guns were loaded exclusively with proximity-fused ammunition. In 90 minutes of continuous combat that pushed gun crews to the absolute limits of human endurance, Hadley shot down 23 attacking aircraft, setting an all-time United States Navy record for aircraft destroyed by a single ship in one engagement. Every proximity-fused shell that came within 70 feet of a target detonated automatically, filling the sky above Hadley with lethal shrapnel patterns that Japanese aircraft could not evade no matter how they maneuvered. The nearby destroyer USS Evans accounted for 19 additional aircraft before being forced to retire after taking multiple kamikaze hits. Together, the two destroyers shot down more than 40 enemy aircraft in one of the most intense naval battles ever fought. Both ships received Presidential Unit citations for this action, and the after-action report filed by the task force commander described the proximity fuse as indispensable for ship survival. But while the Navy was using proximity fuses extensively across the Pacific theater, the Army remained absolutely prohibited from using them over land in Europe. The restriction remained in place through all of 1943 and most of 1944. Army artillery officers knew proximity fuses existed. They had heard reports filtering back from the Pacific. They knew the technology worked under combat conditions. They understood exactly how devastating these shells would be against German ground forces, but Pentagon officials remained convinced that the risk was too great. Even a single dud shell falling into German hands could compromise Allied air superiority over Europe. Germany possessed the most advanced scientific establishment of any Axis power. German universities had produced more Nobel Prize winners in physics than any other nation before the war. German engineers had developed jet aircraft, ballistic missiles, and advanced submarine technologies that Allied scientists were still struggling to understand. If German engineers obtained an intact proximity fuse and reverse-engineered the technology, the consequences could be catastrophic. They might develop countermeasures that could blind Allied radar systems. They might create their own proximity, fused anti-aircraft shells that would devastate the bomber formations flying over Germany every single day. American and British bombers were already suffering horrific casualties from conventional German anti-aircraft fire. With proximity fuses, German flak batteries might make daylight bombing completely impossible. The risk seemed far too great to Pentagon planners. Army, artillery officers would have to wait, regardless of how many American soldiers died because their artillery could not kill entrenched German infantry effectively. That calculation began changing on June 12, 1944. Germany launched Operation Rumpelkammer, the systematic bombardment of London using V-1 cruise missiles. The V-1s were jet-propelled flying bombs, pilotless aircraft packed with high explosives and aimed at civilian population centres. They flew low and fast, approaching speeds of 400 miles per hour at altitudes that made interception extremely difficult. They were too small and too fast for accurate time fusing with conventional anti-aircraft shells. British fighter pilots tried desperately to shoot them down or tip their wings with their own aircraft to send the missiles off course into unpopulated areas, but it was extraordinarily dangerous work, and many skilled pilots died attempting these desperate manoeuvres. The V-1s killed tens of thousands of British civilians, and caused massive structural damage to London. The Pentagon authorized limited use of proximity fuses to defend London against V-1 attacks on June 12, 1944, just hours after the first missiles struck British cities. Initially, the fuses were restricted exclusively to 90mm anti-aircraft guns and British 3.7-inch guns positioned along the English coast, where dud shells would fall harmlessly into the ocean, preventing German recovery. The results were immediate and dramatically exceeded expectations. In the first week of operations with proximity fuses, British anti-aircraft gun batteries destroyed 17% of incoming V-1s. This was already substantially better than the combined 24% success rate achieved with all traditional methods, including fighter interceptions and conventional anti-aircraft fire combined. But as gun crews gained experience with the new fuses and fire control, radar systems improved through practical combat use, the success rate climbed steadily week by week. By the end of the fourth week of operations, proximity fused shells were accounting for 79% of all V-1s destroyed by anti-aircraft fire. By late August, after proximity fuses were widely deployed across the entire defensive belt protecting London, that percentage reached 74% of all incoming missiles intercepted before reaching their targets. On some particularly effective days, the interception rate reached 82%. The Germans launched 9,300 V1s at England between June and August 1944. Without proximity fuses providing effective air defence, the casualties and physical destruction would have been catastrophic beyond measure. The proximity fuse had saved London from what could have been an even more devastating assault than the Blitz of 1940 and 41. British Prime Minister Winston Churchill later wrote that the proximity fuse proved potent against the small unmanned aircraft and credited it with preventing far greater loss of life among British civilians. When V1 attacks shifted strategic focus to the port of Antwerp in Belgium in September 1944, the restrictions on proximity fuse use over land loosened further by operational necessity. Antwerp was absolutely critical for supplying Allied armies advancing toward Germany. The port provided the only logistics hub capable of handling the massive quantities of ammunition, fuel, food, and equipment needed to sustain offensive operations. Losing Antwerp would cripple the Allied advance and potentially extend the war by months. The Germans recognized Antwerp's strategic importance with perfect clarity and redirected their remaining V1 launchers to systematically target the city and port facilities. Between October 1944 and March 1945, the Germans launched more than 8,000 V1s at Antwerp in a sustained campaign designed to destroy Allied logistics capabilities. British and American anti-aircraft units established defensive belts around the entire city perimeter. The British 11th Armoured Division defending Antwerp came under a particularly intense barrage in September that required emergency modifications to anti-aircraft fuses to counter new German tactics. The Crosley Corporation in Cincinnati worked around the clock, running multiple shifts to produce the specialized modified fuses needed for the Antwerp defense. British Prime Minister Winston Churchill personally authorized a special emergency flight of Lancaster bombers to transport the urgently needed fuses from Cincinnati directly to Europe, demonstrating the critical strategic importance attached to maintaining Antwerp's defences against German missile attacks. Once the modified proximity fuses were deployed to British anti-aircraft units, a single gun battery in Antwerp destroyed 48 of the first 75 V1s they encountered, representing a 64% success rate that exceeded all previous defensive performance. With the V1 threat largely mitigated through proximity fuse deployment, the port of Antwerp remained operational for the duration of the war without significant interruption. By the end of the entire V-weapon campaign, anti-aircraft units equipped with proximity fuses had destroyed more than 2,000 V1s, targeting Antwerp and London combined, preventing casualties that would have numbered in the hundreds of thousands. On October 25, 1944, the combined Chiefs of Staff formally authorized general use of proximity fuses over land for anti-aircraft defense purposes, officially recognizing what had already become standard operational practice across the European theatre. But ground artillery units still remained absolutely prohibited from using proximity fuses against enemy ground forces. Army artillery officers were furious about restrictions they considered bureaucratic obstruction that was costing American lives. They knew from classified briefings that proximity fuses would be devastatingly effective against German ground targets. A conventional artillery shell detonated on impact with the ground, which meant that troops in trenches, foxholes, or positioned behind any kind of cover received substantial protection from fragmentation effects. The blast and fragments radiated outward and upward from the point of ground impact, but a shell that detonated in the air 30 to 50 feet above enemy positions would spray fragments downward directly into defensive positions. Trenches became death traps with no overhead protection. Foxholes offered no safety whatsoever against fragments arriving from above. Even heavily reinforced log bunkers that would stop conventional artillery fragments could be penetrated by high-velocity fragments arriving at steep downward angles. Proximity-fused artillery would multiply the lethality of American firepower against entrenched German infantry by factors of 5 to 10 times, but the Pentagon continued to refuse authorization. The risk of a dud shell falling into German hands and being reverse-engineered remained considered too high by strategic planners in Washington. Army artillery commanders would have to continue fighting with conventional ammunition regardless of the tactical disadvantages. Then, at 0530 hours on December 16th, 1944, Germany launched Operation Wacht am Rhein, Watch on the Rhine. 3 entire German armies attacked through the Ardennes Forest in Belgium and Luxembourg, hitting thinly held American positions with overwhelming concentrated force. The attack achieved complete tactical and strategic surprise. German armour punched through American defensive lines and began driving west toward the Meuse River and the strategic Belgian port of Antwerp. The Battle of the Bulge had begun, and American forces were in immediate serious trouble facing the largest German offensive operation on the Western Front since 1940. Colonel George Axelson made his decision to use proximity fuses within minutes of learning about the German attack. His 406th Field Artillery Group had received shipments of POZIT shells just days earlier, the Army code name for proximity-fused artillery rounds that remained highly classified. When the 38th Cavalry Squadron transmitted desperate calls for immediate fire support, Axelson understood that conventional shells would have severely limited effectiveness against German infantry advancing through heavily forested terrain where trees provided natural overhead cover. But proximity-fused shells detonating above the forest canopy would kill anything in the open below regardless of ground cover. He gave the order to his gunners without hesitation: load POZIT rounds. Commence firing immediately. Effect on German forces was immediate and utterly devastating. German infantry caught in the artillery barrage were cut down by airbursts they never saw coming and could not understand. The shells detonated silently 30 feet above their heads with no warning whistle of incoming fire. Fragments rained down through the forest canopy, penetrating winter uniforms and exposed flesh. Soldiers who dove for cover in foxholes found no protection. The attack on the 38th Cavalry Squadron collapsed within minutes. 3 days later, on December 19th, General Dwight Eisenhower formally requested authorization from the Pentagon to use proximity-fused artillery shells across the entire European theater without restrictions. The German offensive represented the largest concentrated attack the United States Army had ever faced in its history. Every possible tactical advantage mattered when American forces were fighting for survival. On December 21st, after urgent consultation, at the highest levels of Allied command, all restrictions were permanently lifted. Proximity-fused artillery shells were released for unrestricted general use against all targets. The timing proved critical for American forces struggling to contain the German breakthrough. SS Colonel Otto Skorzeny's specially trained troops were attacking the town of Malmedy in a coordinated assault designed to seize critical road junctions. American artillery battalions supporting Malmedy's defense fired proximity-fused shells with devastating and demoralizing effect against attacking German formations. The attacking German soldiers found themselves caught in airbursts that detonated overhead with perfect timing and no warning. Some German soldiers, realizing they faced a weapon they could not evade or survive, charged directly into the artillery fire with their hands raised high, screaming "Kamerad," the German word for comrade, desperately trying to surrender before the next barrage killed them. By December 23rd, field estimates suggested as many as 2,000 German soldiers had been killed by proximity-fused artillery shells in just the first few days of their combat use on the European continent. The Germans quickly realized through bitter combat experience that they were facing an entirely new type of weapon that rendered their defensive tactics obsolete. Prisoners of war interrogated by American intelligence officers repeatedly described the profound, demoralizing psychological effect of artillery shells that exploded in the air above them with what seemed like perfect targeting. Traditional artillery fire gave soldiers a brief critical moment of hope when they heard the characteristic whistle of incoming shells. They would hear the sound, recognize the threat, and dive desperately for cover. If they were positioned in a properly dug trench or foxhole, they might survive even if shells impacted directly nearby, because the explosion occurred at ground level, fragments radiated outward rather than downward. But proximity-fused shells detonated 30 to 50 feet in the air directly above defensive positions, without any audible warning. There was no protective cover available against threats arriving from above. There was no warning whistle to alert soldiers to take cover. The shells arrived at supersonic velocity, detonated silently overhead, and rained shrapnel straight down into positions that should have provided protection. German soldiers who had felt reasonably safe in carefully prepared defensive positions were being killed without ever seeing or hearing the threat that killed them. The psychological impact was severe and immediate. Combat effectiveness degraded rapidly when soldiers realized that their training and defensive preparations were completely ineffective against this new weapon. German field commanders became desperate to understand the technology. They offered substantial cash rewards and immediate promotions for any soldier who could recover an intact, unexploded proximity fuse for examination by German technical intelligence. They needed to understand how the weapon functioned so German engineers could develop effective countermeasures or potentially copy the technology for German use. In late December 1944, advancing German forces overran and captured an American ammunition storage dump that contained approximately 20,000 proximity-fused artillery shells. German military engineers immediately transported sample shells to technical analysis facilities in Germany for detailed examination. German engineers opened the shells carefully and examined the fuses with growing confusion. They recognized that sophisticated electronics were clearly involved in the detonation mechanism. They could identify miniature vacuum tubes, battery components, and radio frequency circuits. But they fundamentally could not understand how the technology actually worked under combat conditions. Most critically, German engineers simply could not believe that miniature vacuum tubes could possibly survive the extreme acceleration forces of artillery gun firing. Their own exhaustive research, conducted over more than a decade, had convinced them with absolute certainty that such tubes were physically impossible to manufacture with existing materials and techniques. The German engineers examining captured American proximity fuses assumed the devices must be defective prototypes or designed for some completely different application other than artillery shells. They never realized what they were actually looking at. By the time German scientists finally understood the full significance and functional capability of American proximity fuses, the war in Europe was nearly over, and Germany had virtually no remaining industrial capacity left to develop or manufacture countermeasures. The window of technological opportunity had closed permanently. On the night of December 25th and 26, 1944, General George Patton's Third Army caught a German battalion attempting to cross the Sauer River near Echternach, Luxembourg. The German forces were attempting a night river crossing to outflank American defensive positions. American artillery forward, observers called for immediate fire missions. Artillery units positioned on high ground overlooking the river fired a concentrated barrage using exclusively proximity-fused shells. The shells detonated above the river and above German troops massed on both riverbanks preparing to cross. There was absolutely no cover available on the exposed riverbank terrain. No trees provided overhead protection. No buildings offered shelter. The German soldiers were completely exposed in open terrain. General Patton wrote a letter directly to the War Department in Washington, describing the result in precise tactical detail. "The new shell with the funny fuse is devastating," Patton wrote. "We caught a German battalion, which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." 702 confirmed German dead in a single concentrated artillery barrage. That represented unprecedented lethality that exceeded anything previously achieved with conventional artillery fire. Traditional artillery shells fired at the same target under similar circumstances might have killed 50 or 60 soldiers at most. The proximity fuse had multiplied the combat effectiveness of American artillery by more than 10 times in a single engagement, and this was not an isolated exceptional incident. Throughout the Battle of the Bulge, proximity-fused artillery systematically devastated German formations caught in the open or attempting to maneuver under fire. In the Ardennes Forest, an American chief ordnance officer filed a report describing 96 bodies recovered from a German patrol hit by a massed proximity-fused artillery barrage. "The bodies looked as if they had gone through a meat grinder," he wrote in his official after-action report. The high-velocity artillery shells arrived too quickly for German soldiers to hear them approaching. The air bursts detonated with no audible warning. Foxholes provided absolutely no protection against fragments arriving from directly above. The shrapnel penetrated even log-reinforced bunkers that would have completely stopped conventional ground-burst artillery fire. German units that attempted to advance through areas covered by American proximity, fused artillery fire, were systematically annihilated before reaching their objectives. German unit commanders filed increasingly desperate reports, stating that their soldiers were refusing direct orders to move forward into attack positions because they understood that proximity-fused artillery kill them, even in covered defensive positions. Prisoners of war interviewed immediately after capture described being in a profoundly dazed psychological state after surviving proximity-fused artillery barrages. They realized they were facing a fundamentally new kind of artillery weapon but could not understand how it functioned or how to effectively evade it. Minor mutinies broke out among several German units that received orders to advance into areas known to be covered by concentrated American artillery fire. Some German soldiers simply refused to leave their fortified bunkers when they knew proximity-fused artillery was actively targeting their sector, regardless of threatened disciplinary action. The Germans had felt relatively safe from traditional timed artillery fire because heavy overcast winter weather prevented accurate aerial observation of German positions. American forward artillery observers could not see German defensive positions clearly through cloud cover and fog, which meant timed artillery shells would be set based on map estimates and guesswork that were frequently wildly inaccurate. German troops had learned through experience to take immediate cover whenever they heard artillery fire and simply wait for the barrage to end. Most shells would explode harmlessly because the time fuses were set incorrectly. But proximity-fused shells did not require any accurate visual observation of target positions. The fuses automatically detonated at optimal height above ground, regardless of weather conditions, visibility limitations, or time of day. American gunners only needed to know the approximate grid coordinates of German force concentrations and fire in the general direction. The proximity fuses autonomously handled all targeting decisions, detonating at precisely the right moment to maximize fragment effectiveness. The bad weather conditions that had previously protected German forces from accurate artillery fire now meant absolutely nothing against proximity-fused ammunition. German tactical doctrine had to be completely rewritten, but there was no time during active combat operations to retrain forces or develop new defensive procedures. By late January 1945, German resistance in the Ardennes had collapsed entirely. The Battle of the Bulge was conclusively over. American forces had stopped the largest German offensive of the entire war and were actively preparing to cross the Rhine River into Germany itself for final offensive operations. Proximity-fused artillery had played a critical and possibly decisive role in that victory. General Patton later publicly stated that the funny fuse won the Battle of the Bulge for us. While that assessment represented a clear overstatement that ignored countless other factors contributing to Allied victory, the proximity fuse had undeniably and fundamentally changed the tactical situation on the ground. German forces that would have been able to defend prepared. Positions effectively against conventional artillery fire were systematically wiped out by airbursts they could neither avoid nor survive. In the Pacific theatre, the proximity fuse had an even more strategically dramatic impact on the course of naval warfare. By 1945, Japanese military forces had widely adopted kamikaze tactics, using suicide aircraft loaded with high explosives to deliberately attack American ships. These attacks were extraordinarily difficult to defend against using conventional weapons because traditional anti-aircraft fire required direct hits on aircraft that were deliberately and determinedly trying to crash into ships at extremely close range. Kamikaze pilots often approached American ships at wave-top altitude, making early visual detection extremely difficult, until the attacking aircraft was already dangerously close. They would then pull up sharply for their final terminal dive, giving shipgun crews only seconds to engage effectively before impact. But proximity-fused shells created an autonomous defensive barrier around American ships that was almost impossible for kamikaze aircraft to penetrate, regardless of pilot skill or determination. The shells did not require direct hits on maneuvering targets. A near miss was functionally as lethal as a direct hit because the proximity fuse would detonate automatically whenever the shell passed within 70 feet of an aircraft. Navy operational studies conducted after major battles showed conclusively that ships using proximity-fused ammunition were 5 to 10 times more effective at stopping kamikaze attacks compared to ships firing conventional time-fused shells under identical combat conditions. Ships equipped with 5-inch 38 caliber guns firing proximity-fused ammunition could create a lethal defensive zone extending thousands of yards from the ship in all directions. Any attacking aircraft entering that defensive zone faced a statistical probability of destruction that approached mathematical certainty with multiple gun mounts firing simultaneously. Admiral Arleigh Burke, who commanded destroyer squadrons in the Solomon Islands campaign during 1942 and 1943, later wrote extensively about the extraordinary difficulties of defending against Japanese air attacks, especially during night operations when visual targeting was nearly impossible. Mechanical time fuses, which we had been using, only brought down a plane at night by accident, he recalled in post-war interviews. They were good for harassing enemy aircraft at night to disrupt their attack approaches, but that was about all they actually accomplished. The proximity fuse changed everything by making nighttime air defense genuinely effective for the first time in naval history. In the 7 months from January to July 1945, American ships expended nearly 2/3 of all proximity fuses used during the entire war, shooting down more than 200 Japanese aircraft during the Okinawa campaign alone. The proximity fuse technology allowed the Navy to maintain sustained offensive operations in contested waters, where kamikaze attacks would otherwise have made naval operations suicidally dangerous and operationally impossible. The effectiveness of proximity fuses went far beyond simple statistical kill ratios. The psychological impact on enemy forces proved significant and measurable through intelligence reports. Japanese pilots understood clearly that approaching American ships equipped with proximity-fused anti-aircraft guns meant flying directly into an invisible sphere of certain death. The shells did not need to hit their aircraft directly to kill them. The shells just needed to pass reasonably nearby and detonate automatically. There was fundamentally no way to evade this autonomous defensive system through superior piloting skill or tactical maneuvering. Japanese pilots who survived kamikaze missions reported feeling completely helpless against weapons that seemed to anticipate and counter their every maneuver. The proximity fuse demonstrated a fundamental pattern that would repeat throughout World War II and continue influencing military technology development for the next 80 years. Technological advantage in warfare does not come primarily from theoretical scientific breakthroughs or individual genius. It comes from disciplined engineering execution, systematic problem-solving, and manufacturing capability at industrial scale. The basic concept of a proximity fuse was well understood by multiple nations before the war even began. British, German, and American scientists all understood the theoretical physics involved. What ultimately separated success from complete failure was the practical ability to solve thousands of small, interconnected engineering problems, manufacture precision components to exacting tolerances, and produce complex electronic devices in quantities of millions, while maintaining rigorous quality control at every stage of production. The United States possessed the industrial base, the skilled technical workforce, and the organizational management structure that could effectively coordinate sophisticated work across dozens of independent contractors, operating hundreds of facilities. Germany and Japan simply did not possess equivalent capabilities by 1944. By the middle of 1944, American industry was producing more proximity fuses every single month than Germany and Japan had produced artillery shells of all types combined during the same period. The industrial disparity was overwhelming and insurmountable. General George Patton had been absolutely correct when he wrote to the War Department that armies would need to devise entirely new methods of warfare once proximity-fused artillery became widespread and universally available. The fundamental tactical assumption that soldiers positioned in trenches or foxholes were reasonably safe from artillery fire had been central to military doctrine since World War I. The proximity fuse completely shattered that 2-decade-old assumption. Defensive positions that had been considered adequate protection against conventional artillery were suddenly transformed into death traps that provided no meaningful protection. Armies would need to disperse much more widely across terrain, dig substantially deeper fortifications with overhead protection, and move much faster to avoid concentrated artillery barrages. The tactical changes forced by proximity-fused artillery rippled through military doctrine and training for decades after the war ended. Section T operated throughout the war on an accelerated development timeline that would have seemed completely impossible during peacetime with normal bureaucratic processes. From the initial project assignment in August 1940 to the first combat use aboard USS Helena in January 1943, represented less than 2.5 years of total development time. During that extraordinarily compressed period, Tuve's team had successfully solved technical problems that had completely stumped scientists in multiple countries for more than a decade of previous research. They had developed miniature, ruggedized vacuum tubes that could survive mechanical forces no civilian electronics had ever been designed to withstand. They had designed complex circuits that operated reliably under conditions of extreme vibration, radical temperature variation, and intense electromagnetic interference. They had created entirely new manufacturing processes that could produce sophisticated electronic devices at scales previously thought impossible by industrial engineers. And they had accomplished all of this while maintaining absolute operational secrecy that successfully prevented enemy intelligence services from learning what was being developed. Dr. Merle Tuve never received significant public recognition during the war for leading the development of the proximity fuse. The entire project remained highly classified until after Japan surrendered in August 1945. Even after the war formally ended, Tuve remained characteristically reluctant to discuss his personal role in the project. He understood clearly that Section T had solved a critical engineering problem that saved thousands of Allied lives and contributed materially to shortening the war. But he also understood that many talented people working at many different organizations had contributed essential work to that collective success. The proximity fuse was definitely not the product of a single genius inventor working in isolation. It was the product of systematic large-scale collaboration between physicists, engineers, manufacturing specialists, and military personnel across dozens of organizations spanning the entire country. Over 22 million proximity fuses were produced during World War II by more than 100 different manufacturing companies. That unprecedented scale of precision electronics production required essential contributions from thousands of individual workers, most of whom never knew exactly what they were building or how it would be used in combat. After the war ended, Tuve quietly returned to the Department of Terrestrial Magnetism at the Carnegie Institution and served as its director from 1946 to 1966. He continued his pre-war research in geophysics and radio astronomy. In 1948, he was named an honorary Commander of the Order of the British Empire for his exceptional service to the Allied cause during the war. President Harry Truman personally awarded him the Presidential Medal for Merit, but Tuve rarely spoke publicly about his proximity fuse work even decades later. When occasionally asked about his wartime contributions, he consistently emphasized the collaborative nature of the entire project and the critical contributions of the engineers and manufacturing technicians who had solved countless practical technical problems that made mass production possible. Dr. Merle Tuve died on May 20, 1982, at the age of 80. His obituaries mentioned his important contributions to geophysics and his wartime leadership of the Applied Physics Laboratory, but most newspaper accounts did not detail the specific nature of his work on proximity fuses. The technology had been declassified for nearly 4 decades by that time, but it remained relatively obscure outside specialized military and technical circles. Tuve himself had never sought publicity or recognition for his wartime accomplishments. He believed deeply that scientific achievement should be measured by practical results and positive impact, not by personal recognition or fame. The proximity fuse had saved countless lives and helped win the war. That outcome was what truly mattered. The Applied Physics laboratory that Tuve founded in 1942 continues operating today as a major research facility affiliated with Johns Hopkins University. It conducts advanced work in national security applications, space exploration technology, and cutting-edge weapons development. The original building in Silver Spring, Maryland, where Section T first assembled prototype proximity fuses in 1942, no longer stands. It was demolished decades ago and replaced by standard commercial development. There is no historical memorial marker at the site. Nothing visible identifies it as the place where one of the war's most important and influential technologies was born. The factory workers who assembled millions of proximity fuses in facilities across America returned to their peacetime jobs and normal civilian lives when the war ended. Most never learned exactly what they had been building during those intense wartime years. The soldiers and sailors who directly benefited from proximity-fused ammunition rarely understood the technical details of how the fuses actually functioned. They only knew from direct combat experience that anti-aircraft guns were suddenly dramatically more effective and artillery barrages were far more lethal against enemy forces. The technology remained somewhat mysterious even to the people whose lives it directly saved. The 702 German soldiers killed by proximity-fused artillery fire on the banks of the Sauer River in December 1944 were buried in military cemeteries scattered across Luxembourg and Germany. Their grave markers do not mention specifically how they died. The official military records simply list them as killed in action by artillery fire, which was technically accurate but profoundly incomplete. They were among the very first ground troops anywhere in the world to be killed by a technology that their own nation's best scientists had carefully examined and confidently declared physically impossible to build. They died without knowing that the shells exploding invisibly above their heads contained miniature radar sets more sophisticated than anything Germany had been able to manufacture. They died without understanding that American factories were producing these technologically advanced shells by the hundreds of thousands every week, while German industry desperately struggled to manufacture even basic conventional time and spite artillery ammunition. The German engineers who had officially declared proximity fuses impossible never fully understood what critical factors they had missed in their analysis. After the war ended, American technical intelligence teams systematically interrogated captured German scientists and showed them previously classified German documents detailing their extensive proximity fuse research programs. The Germans had actually explored most of the same technical approaches that Section T had ultimately used successfully. They had carefully considered radio, frequency fuses, various vacuum tube designs, and multiple miniaturization techniques. But German researchers had reached a definitive conclusion that the fundamental engineering challenges simply could not be overcome with existing technology and available materials. What ultimately separated the successful American project from the failed German project was not any significant difference in theoretical scientific knowledge or conceptual understanding. The critical difference was in sustained engineering persistence, iterative problem-solving methodology, and overwhelming manufacturing capability. American industry could produce miniature ruggedized vacuum tubes in quantities of millions with consistent quality. American engineers could systematically iterate through dozens of design failures until they eventually identified solutions that worked reliably under all conditions. Germany completely lacked the industrial base, the available time, and the necessary resources to compete effectively on those terms by 1944. British scientists who had contributed the initial circuit designs and theoretical concepts to Section T during the Tizard mission watched American success with distinctly mixed feelings. They had successfully solved many of the core conceptual problems, but had been completely unable to scale up to industrial mass production. The British proximity fuse program produced functional working prototypes that demonstrated the concept was achievable, but never achieved the reliability and cost-effectiveness needed for large-scale military deployment across entire fleets and armies. When the Tizard mission delivered British proximity fuse designs and prototypes to Section T in August 1940, they provided Americans with an invaluable starting point and proof that the concept could work. But as Tuve later noted in post-war technical conferences, the final circuit design that Section T successfully made work under combat conditions was substantially and fundamentally different from the original British design. American engineers had systematically redesigned nearly every single aspect of the fuse to meet exacting Navy specifications and survive the absolutely brutal mechanical forces of artillery gun firing. This is ultimately how wars are actually won in practice. Not through dramatic sudden breakthroughs or individual genius inventors working in isolation, but through systematic, disciplined collaboration between scientists, engineers, manufacturing specialists, and military personnel who understand operational requirements. The proximity fuse succeeded because Section T could draw effectively on the vast resources of American industry, the concentrated technical expertise of academic researchers, and the practical operational knowledge of Navy ordnance officers who understood exactly what combat conditions would demand from the weapon. It succeeded because Western Electric and Raytheon could manufacture ruggedized vacuum tubes that no one had ever built before. It succeeded because factory workers across America could assemble complex precision electronics at scales that would have been completely impossible for any other nation to achieve. And it succeeded because Colonel George Axelson made the critical decision to use the technology when it mattered most, even though he was directly violating explicit orders by doing so. The story of the proximity fuse is fundamentally the story of American industrial and scientific capability at its absolute peak. It is the story of what becomes genuinely possible when brilliant, talented people are given clear objectives, adequate resources, and reasonable freedom from bureaucratic constraints. It is the story of innovation that happens not through individual genius, but through systematic problem-solving at unprecedented scale. And it is the story of a technology that saved thousands of Allied lives and permanently changed warfare forever, developed by people whose names are mostly forgotten today. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.